This is a video for Algebra 2 Common Core, Logarithms Day 6, Solving Log Equations. We're going to start actually with this warm-up that has to deal with graphing logarithmic functions. We haven't done much with graphing logarithmic functions actually on graph paper, but that is something that they could feasibly ask you to do on the Regents, so it would be a good idea to practice that. So it says to consider the function h of x is equal to log base 2 of x plus 8. And then it says to algebraically determine the domain of h of x. So we recently discussed the domain of logarithms and how you can't take the log of a negative number or 0. So if I want to know what the domain of my logarithm is, I'm interested in what's on the inside of these parentheses, and I have to make sure that that stays greater than 0. So I'm going to take x plus 8 and set it to be greater than 0, and then I can quickly solve that, and we end up getting x is greater than negative 8. It doesn't say to write it in interval notation, but we can because it's good practice. All right, so all x is greater than negative 8 means I'm going from negative 8 to infinity, right? Not including that negative 8 in my domain, and that's actually a clue for my graph, right? That means that there's actually going to be an asymptote at x equals negative 8 on my graph. So that's a helpful tip for later. Part B says to graph it on the axis provided with a hint, and anytime we want to graph something, we can use our graphing calculator to come up with the table. So they've given us a table that has some x values, and we want to fill in the y's. So I'm going to pull up my graphing calculator software thing here. It works pretty good, it's just a little slow. But I want to get this equation into my y1, right? Log base 2 of x plus 8, so I can look at the table. If you have a newer calculator, right, we can use the log base trick, which is helpful. If you have the older calculator, right, and you want to type that in, then you have to use the change of base rule and do log of x plus 8 divided by the log of 2. But, say most of you have the newer calculators, so that's good. So I'm going to go over to math. I'm going to go down and find the log base. Try not to click too many times. Okay, so there it is, log base. And then it pops up nicely here. Right? And we can put in 2 for the base. And then over here I can do x plus 8. Okay, and then I'm going to go look at the table. So second in graph to go look at the table. And then it starts at negative 8. So I'm going to click down a little bit. I can see 0. Not going too far. Okay, so there's an error at negative 8. Right, and then I can fill in the rest of my table. So error there, negative 7, 0, negative 6, 1, 1.585. Negative 4 goes with 2. And I've got 2.3219. 2.585, 2.8074, and then when x is 0, the y value is 3. Okay, and I can look at this picture quickly before I graph my points. Right, there's the curve of the log graph, right, and it's a little weird because it looks like it stops there. It really doesn't. There's a horizontal asymptote. And you have to know that that's happening and how to properly draw the graph. So I can go over to my graph paper now and graph these points. All right, so again, this negative 8 error business means that there's actually going to be an asymptote, 1, 2, 3, 4, 5, 6, 7, 8, over here at x equals negative 8. Right, so we can dot that in. So there's an asymptote there. And then I can plot these points. So negative 7, 0, negative 6, 1, negative 5, 1.585-ish there, negative 4 and 2, okay, negative 3, 2 and a little bit, negative 2, a little higher, okay, oops, getting closer to that 0, 3 there. Okay, and then, say, from what we know about asymptotes, right, we know that it's going to kind of skim down this way and head towards that asymptote. Oh, that was a terrible graph. Okay. Let's try that again. Towards the asymptote, and then it's going to come up this way and keep creeping upwards like that. Okay, close enough. Pretend it goes through this point right here that I missed right in the middle. All right, so that's our graph. Okay, then there's a couple questions down here. Some good review, right? What transformation applied to f of x equals log base 2 of x would produce this graph? So just a regular log graph, remember, right? Our basic log graph has an asymptote. Instead of it y equals 0, it's a vertical asymptote here at x equals 0. And then it's got the x-intercept at 1, 0, and it swoops up like that. Then it's the inverse of an exponential. So our log graph, instead of going through 1, 0, is now going through here at -7, 0. Right, so that means it's been translated to the left 8 units. And so translated to the left 8 units. And then Part D and Part E asks about the x and the y-intercepts. And we've done this all year long. So x-intercept is all about when the y is 0. Y-intercept is all about when the x is 0. Okay, now we can also easily see these from our graph. Right, so when y equals 0 in my table, that corresponds to x equals -7. Right, I can see that from my picture. I can see that from my table. So that means my x-intercept is going to be -7, 0. I can find that algebraically as well. If I take my equation, log base 2 of x plus 8, and I plug in 0 for y, log base 2 of x plus 8. If I now think about solving this equation for x, this is a pretty basic one. We're going to do some more work with solving log equations in a second. I know I can get rid of the log by exponentiating. So I'm going to do base 2 to both sides and cross that out. 2 to the 0 is 1 equals x plus 8, and then I can solve it and get my x equals -7. So several ways to figure out that x-intercept, and if you didn't have the picture, you could do it algebraically. And then the same sort of thing with the y-intercept, right? The y-intercept is all about when x is 0. So in my table, I can see I've got the point 0.03. On my graph, I can see I've got the point 0.03. All right, so when y equals 3, so I've got 0.3 for my y-intercept. And I could find that algebraically as well. If I take my equation and I plug in 0 for x, right, I end up with y is equal to log base 2 of 8. And remember, log is just asking you, what exponent do I put on 2 to give me 8 as the answer? The answer to that is 3. So we can find it algebraically as well. Okay, so that's a little bit about graphing logs, should that come up at some point later in your life. All right, let's switch over now to the day 6 notes. Okay, so we should have this worksheet for solving logarithmic equations. So this is going to put together a lot of the stuff we talked about in this unit already. We've already discussed that, if you have an equation that has an x in it and a log involved, that we basically want to get rid of the log. That's the only way to solve it. So we've laid a lot of the groundwork here already. If you scroll down, these are some fairly complex equations in that there's just a lot going on, which means that we're going to actually make use of our log properties. So the steps to solving the log equations are listed out up here. So we're going to use our log properties to basically condense our equation on each side so that there's no more than one log on each side of the equation. Then we know we can get rid of the logs by exponentiating, so we'll do that. And then we'll be left with some equation that doesn't have a log in it that we'll be able to solve. And then the trick is we have to make sure to check our answers, right? We may have to reject them if they're not in the domain. Reminding you again that we can't take the log of a negative number or 0, right? Because 0 is not in the domain. So we'll have to check our answers at the end and make sure that we don't have to reject anything. Okay, but here are some equations, and we'll put this to work. So first one, I've got log base 3 of 2 is equal to log base 3 of 2 plus log base 3 of 7 equals log base 3 of x. So Our log properties, think back to a few days ago, if I have logs being added together, again, where did that come from to condense it back together, right? Multiplying, log of two things multiplying is what would produce the two logs being added together. So I'm going to condense that left side back together. This is really log base 3 of 2 times 7 is equal to log base 3 of x. And then I can clean that up and multiply inside my parentheses here. So now I've got log base 3 of 14 is equal to log base 3 of x. Okay, now I've got it so that there's only one log on this side and only one log on that side. That's the goal. So once that happens, I can get rid of my log, right? They have the same base. So that means I can get rid of them by doing the exponentiating. So I'm going to introduce 3 as a base. Right? So 3 to both sides. 3 log 3 crosses out there, and I'm left with 14. 3 log 3 crosses out there, and I'm just left with x. And then I'm basically done. This one was super easy. Right? One thing to check before we box in our final answer is, again, I have to make sure that this answer that I get for x, when I plug it in here, is not going to break my log rules about ending up taking the log of a negative or 0. So the only place where there's an x is right here. Am I allowed to plug 14 in there? Sure. I don't know offhand what this is. 3 to what power gives me 14? It's not going to be something nice, but it is something that exists, right? It's not breaking the rule. This is not 0 or a negative, so it's fine. Okay, so that is going to be my answer there. We could also check this on our calculator, and we do have the ability to do that as well. And we can solve any equation graphically. Some are easier than others. Just rewriting this here. Log base 3 of x. So if I wanted to solve it graphically, oops, that didn't quite work out there. Okay, log base 3 of x, there you go. So I know I can put one side of my y1, the other side of my y2, and look for that intersection point. So let me pull up my calculator again. Okay, so I'm going to clear out this guy here. Okay, so I want to put this side into my y1, so I'm going to go back and find my log base. I'm going to go from the bottom up here. Okay, so log base 3 of 2 plus, okay, another log base. And again, if you have the older calculator, you would have to use your change of base rule here and do log of 2 divided by log of 3, and then plus the log of 7 divided by log of 3. So you can do that if you have the older calculator, and you can't do log base. Okay, so I've got my y1, and then in my y2, I will put log base 3 of x. Okay, and then I will graph this. Right, ready to do a sketch to show my work. It's a little slow to graph. Okay, graphing that horizontal line. There you go. And then we should see the log curve come up. Okay, and I'm looking for the intersection point, and sadly it's over here somewhere, right, which I can't see now. We already happen to know the answer is 14, right? So, but if we didn't know that, so I gotta go over to the window. I'm gonna make my x max bigger. So let's try 20. I'm going to mark that on my sketch. Okay, here comes the very slow horizontal line again. Graphing, graphing, graphing. And then there comes the log curve. Okay, and now we can see that intersection point. Okay, and we're pretty good at doing sed calc intersect, so I think I'll skip that part. All right, but if you do sed calc intersect there, that comes out to be 14 and about 2.4. And so there's your x equals 14. So you can check it that way too. So you can graph the logs. Right, easier if you have the log base, but if you have to use the change of base rule, you can do that as well. Okay, let's look at some more equations. Moving on to number 2. So now I've got the log of x plus 2 plus the log of x plus 5 is equal to 1. Okay, so again, if I have the log of two things, or two logs being added together, right, from my log properties, right, that came from x plus 2 being multiplied by x plus 5 inside of the log, right, because then that would break down into log of x plus 2 plus the log of x plus 5. So I put those together. Okay, I'm going to clean this up inside of here and multiply that out. So x plus 2, x plus 5, oops, didn't really need that, that's okay. 5x, 2x, and 10. Okay, so now I really have the log of x squared plus 7x plus 10 is equal to 1. Okay, so I've got one log on this side and no logs on the other side, but that's fine, right? You might have just one log on one side and no logs on the other. The key is you can't have more than one log on each side. So I do have this log that I'm going to get rid of by exponentiating using the base. Say, what's the base on this log when we don't see a base there? Remember, that's implied to be base 10. So I'm going to exponentiate using base 10, and I got to do that to both sides. So the 10 to the log crosses out, and I have x squared plus 7x plus 10. And then on this right-hand side, I would have 10 to the first, right, which is just 10. Okay, now I've gotten rid of the log. This is just a quadratic, and we've solved a lot of quadratics. So actually, if we bring that 10 over, it's going to cancel out, right? So just get x squared plus 7x equals 0. Do a little factoring here, take out a GCF. Okay, so I end up with x equals 0, and then x equals negative 7. And then before we box them in, we got to check. Right, so I want to make sure when I plug this 0 in, I don't take the log of something that I'm not allowed to. So if I plug 0 in here, I would end up with the log of 2, which is fine. Again, it's not going to be nice, but I can do it, right? And also the log of 5, which again is 5. Which is fine. So x equals 0, that's okay. When I look at negative 7, though, right, and I try to plug that in here, I'm going to end up with the log of negative 5. Okay, that's no good. You can't take the log of a negative number. So x equals negative 7, that cannot be an answer because when we plug it in, that's not in our domain. Okay, so we got to reject the negative 7. So the only solution here is x equals 0. Yeah, you could check this for real graphically, or, plug it in and check the numbers, and you absolutely got to check the domain thing. If you want to do further checks on that, you can too. Okay, one more here on the front side. Log of x is equal to 3 times the log of 2. So this number that's here in the front, and where did that come from? Thinking about log properties, right? A coefficient that's out in the front really came from an exponent that was up here. So I'm going to rewrite this. This is really the log of x is equal to the log of 2 to the third. Whether you put it on the inside of the parentheses or on the outside of the parentheses, it doesn't really matter. It's going to end up being the same thing. Okay, but that was really all I had to do. I've got one single log on both sides. Now I can get rid of the logs by exponentiating. I'm going to use base 10 again. A log with no base is base 10. So that crosses out, and that crosses out. So I get x equals 2 to the third, all right? Or x is equal to 8. I could have really done that up here. Probably should have. Right, either way, you end up with x equals 8. Sorry, I did that kind of weird. Okay, probably should simplify inside the parentheses and then get rid of it. But either way, you end up with 8 there. Okay, and then I should have checked that too. Right, but I could plug in 8. That's not going to give me any trouble in terms of taking the log of a negative or 0. Okay, so that one will just say if you have coefficients in front, right, those came from exponents. Okay, a few more over on the back. They really don't get much trickier, so that's good. Just mainly practice of our log properties and our exponentiating. Okay, over on the back, I see some ln, natural log. I have ln of x plus 2 is equal to ln of 12 minus the ln of x plus 3. Okay, so if the logs are being divided, the logs are being subtracted, that means it came from 2 logs being divided, right? Or the log of 2 things being divided. So I'm going to rewrite this, save some room, I'm going to do it over here. And so this is really ln of 12 divided by x plus 3. Right, so again, how would we break this down? Oh, ln of 12 minus the ln of x plus 3. So I just condensed it back together. Okay, I got one single log and one single log. That means I can get rid of those now by exponentiating. ln, right, what base is that? How do I get rid of an ln? Right, ln is really log base e. So I'm going to use e here. So I'm going to exponentiate both sides using an e, but then e to the ln is going to cross out. So I'll just have x plus 2, and then e to the ln is going to cross out over here, which leaves me with 12 over x plus 3. And so the log part of this is done, and now it's just basic algebra. All right, if I want to solve this equation, you can put this over 1 and cross multiply, or multiply both sides by the denominator. We're pretty good at that. All right, so I multiply over there, those cross out. Okay, you gotta multiply x plus 3 times x plus 2. It's 3x and 6. Okay, so this is really x squared plus 5x plus 6. Over here I would have 12. And we find ourselves again with a quadratic, our favorite. So x squared plus 5x minus 6 equals 0. Okay, I'm going to factor this. Careful with the 5 and the 6. You will always mess this one up, right? It's either 3 and 2 or 6 and 1. If this is a negative and I got to end up with a positive 5, it's got to be 6 and 1. And so x plus 6, x minus 1 equals 0. So I get x equals negative 6 and x equals 1. Okay, but then I got to check them. Right? And again, I always got my eye on that negative, and sure enough, when I plug it in, if I try to plug in negative 6, I'm going to end up trying to do the ln of negative 4. Right? Can't do that. Okay, so we got to reject the negative. And there is no hard and fast rule, though, that negatives always get rejected and positives always work. Believe me, if there's some sort of shortcut like that, I would tell you, but there's not. You got to check them every single time. Okay, but that negative definitely doesn't work. Okay, when I want to plug in a 1, right, I would get ln of 3. That's fine. And then if I plug in a 1 here, it would be ln of, 12 over 4, so, or 12 over 3, which ends up getting 4 again. No, wait, that was right. 12 divided by, yeah, you get ln 3 both times. Oh, because they're equal to each other. That's weird. Okay, either way, it's fine. Okay, just a little mistake in my notes there. So that should end up being, both of those are okay. Or just 1. Sorry, x equals 1 is the answer. Okay, couple more. Log base 2 of x plus 5 minus log base 2 of x minus 2 equals 3. Okay, so logs being subtracted. Logs being subtracted comes from the log of two things divided. So log of x plus 5 over x minus 2 is equal to 3. Okay, I've got my single log, which I can get rid of now by exponentiating using base 2. So 2 log 2 crosses out. X plus 5 over x plus 5 over x minus 2 would then be equal to 8. And then, again, I just have this equation with a fraction in it that we can solve just like we did the previous one. All right, multiply both sides by the denominator. Those cross out. So I end up with x plus 5 equals 8x minus 16. And then if we rearrange some things, 7x over there, 21 over there, we end up with x equals 3. Now mainly we've just been plugging these in, right? I could plug this in and that's a positive. I could plug this in and that's, log of 1, so that's all fine. Every once in a while though, if you look at what happens when you actually go to plug this 3 in, right? I get log base 2 of 8 minus log base 2 of 1, right, equaling 3. And we can actually check this pretty easily. This is a good review of our logs, right? What is log base 2 of 8? What exponent do I put on 2 to get 8? That's just 3, right? What exponent do I put on 2 to get 1? That would be 0, right? And sure enough, that does in fact work. So, yeah, not only does it not break our domain rules about taking the log of a negative or 0, but we can actually check that one easily to show that it does in fact work. And sometimes you can do that. Okay, moving on to number 6. The log of 2x plus 5 squared is equal to 4. So when I see this right off the bat, I'm like, oh, there's just one log here on this side. So I don't really have to do anything. I can just go ahead and get rid of it, right? It would have base 10, so I could exponentiate on both sides with a 10 and get 2x plus 5 squared. 10 to the 4th power is going to have 4 zeros there, so 10,000. So I've gotten rid of the log part. And now this is a quadratic, right? I got to multiply out 2x plus 5 times 2x plus 5, so we can do that. I can fit it in on the side here. And so just multiplying out 10x and 25. Okay, so this would be 4x squared plus 20x plus 25 is equal to 10,000. And then if you subtract that 10,000 over, oh boy, this is starting to look not too pleasant here. 99.75 equals 0. Ew. Okay, so, I'm not sure about factoring this. I could use a quadratic formula, right? And you could do that and it would be fine. But there's a better way, right? There's a better way using our log properties. So, so I said off the bat we didn't have to do anything, and that was true. However, right, if I had done something differently when I started this would be a lot easier, the solving part. And the thing to do, I'm just going to rewrite it here, is to look at that 2 exponent, right, and say, oh, okay, I can use my log properties actually to bring this down in the front, right, and make this be 2 log of 2x plus 5 equals 4. And then if this 2 is just multiplying by this log, I can very easily divide that out, right, and now I've gotten rid of that exponent. And now this is just log of 2x plus 5 is equal to 2. And that's much easier to solve, right? Now I can exponentiate with my base of 10. Right? So 2x plus 5, 10 squared is 100. And then if I subtract and divide, so it doesn't come out nice, right? You could leave it as 95 over 2, or you could leave it as 47.5. Again, it doesn't really matter. As long as it's a terminating decimal, it's okay. So generally, we try to avoid the decimals, though, just so we don't have that issue. So I leave it as 95 over 2. And you can check it, too. I said I should have checked it before I boxed it in again. Right? When I plug this 95 over 2 in here, 2 times 95 over 2 is actually going to give me 95. And then I would add 5, and it would give me 100, right? Which is perfectly fine. So that does work out there. Again, that avoids the whole ugly quadratic formula business. So sometimes it is useful to make use of those log properties going the other way, because it saves us some work. Just be on the lookout for that. Okay, one last one here, going back to sort of this condensing idea. Log ln of this quadratic, right, minus the ln of x plus 4 equals 0. So, again, logs being subtracted comes from logs being divided. So I'm going to do ln of x squared plus 7x plus 12 divided by x plus 4 equals 0. And then I've got my one single log right now. Right, so I can go ahead and exponentiate. ln means I'm going to use base e. So base e and base e, so those cross out. So I just have this fraction, plus 12 over x plus 4. E to the 0 is 1. And then, again, it's similar to what we did before. So I'm going to multiply both sides by that denominator, right, which crosses out. So I'm going to have x squared plus 7x plus 12 is equal to x plus 4. So now I just have a regular quadratic. Right, set that equal to 0. X squared plus 6x plus 8 equals 0. I can factor this. X plus 4 and x plus 2 equals 0. It's down a smidgen. So I end up with x equals negative 4 and x equals negative 2. Okay, so 2 negative answers this time. Oh boy. You know, they could be right, they could be wrong. There's no way to know, really, unless you check. So I'm going to think about plugging in negative 4. I could plug it in here, although I happen to notice if I plug it in here, right, I would actually get ln of 0. And that's already no good, right? Cannot take the log of 0, that's not allowed. So negative 4 has got to go, right? That one does not work. If I plug in negative 2, again, maybe I'll start with this one first because it's easier. All right, if I plug in negative 2 there, I would end up by doing the natural log of 2, which is fine. And then if you go to your calculator and you do -2 squared plus 7 times -2 plus 12, it also comes out to be 2. So that one's also fine. So even though this x is a negative, it actually does work because when you plug it in, you don't end up taking the log of a negative number. So it's okay. So that there's no hard and fast rule there. You just have to check them and see which ones work and which ones you have to reject. So x equals -2 would be our solution there. Again, any of those we did previously, you could check them on the calculator as well. And that is the end of Logarithms Day 6.